In this video, I want to show you a Excel file that I created that calculates the our radio operating curve, ROC curve, for a logistic regression, and also developing the model from data that's given to us. And here on this sheet, you see the credit card, and this problem involves given data of credit card applicants. We wish to develop a model by which we can accept or reject credit card applicants based upon their past performance of and history of other applicants which have defaulted. So we're giving data of age, the years that they've been at their employer, the years at their address, their income, their credit card debt, their automobile debt, and then a factor that I added was debt to income ratio, which I just added the credit card debt and auto debt and divided by the income, and that proved to be a very good factor. And then here's one I added which didn't pay out too good: income plus the card plus the auto debt divided by the age times the years of employment, and years at the address, and that didn't turn out to be that beneficial. And then in the data, we're giving the outcome with a default. If they defaulted on their credit card bill, it was given a 1. So, and a 0 if they did not default. So here's our raw data. Now, in this method, a 1 is a default. So in all these factors, we want to have an increasing factor tends to be a 1. So we found that increasing age, larger ages, really makes the outcome more of a 0 than a 1. So I've highlighted the factors in yellow that we want to reverse. And we can simply reverse these by multiplying the standardized data by a -1. And that way reverse the direction so that an increasing factor makes it more likely to have a 1. And I've had to do this on years at address. Let's see. Years at address, years at employer, employee, and and income. So we just said that a person is less likely to default if they have a large income. So we want to get that in the right direction or matching direction. So and years at address, the longer a person has lived at a certain address, you'd think they'd be more stable and less likely to default. And years at employer, same thing. And the older applicant is less likely to default than a younger applicant, just by common sense. So these marked in yellow are later going to be reversed. But the original data also had, they gave debt as a negative value, and I changed that to be a positive because just to keep from getting so confused, we're later going to standardize the data by taking the mean and dividing by the standard deviation. So it gets a little hard to understand if we have negative averages that we're subtracting from the individual data. So to keep that simple, I have multiplied the credit card debt and the automobile debt that was given in the original data by -1. So I've got positive debt. After all, we're calling it debt, so why not just make it a positive number? And so I took these debt to income ratios here. I simply added the credit card and automobile debt and divided by the income. And this I did the same thing for this factor with the raw data, except the raw data did have these negative values for auto and card debt. So okay, so the next thing I do is to standardize the set. We call this our training set. And here I got the average is in cell B213 and the standard deviation in B215. I did that at the bottom. There's that was done over here on this original set. So I simply standardize the set by subtracting the mean and dividing by the standard deviation. And that what that did was it made all of them in the same magnitude range. And that really helps as far as doing the calculations so things don't, might say, get out of hand. So there's our standardized data. And then and in our ROC curve calculation, we're going to use a max set point of 3.5 and a lower set point of minus 3.5. So all these factors I've manipulated them so that they are between minus 3.5 and plus 3.5. And that's done pretty easy by, it's kind of like a stochastic calculation. If you take the value and subtract the minimum from it and then divide it by the max minus the minimum, you convert all your data to be between 0 and 1. And since the new range, we're going to want a range of 7, I multiply by 7 and subtract 3.5. And that does a 3.5 transformation on the data that places it between minus 3.5 and 3.5. So let's see. So here I've done the 3.5 transformations, and I've also reversed the so that we're increasing factor is increasing from 0 to 1 on the outcomes. So here I made a model, and the model was simply years at employer reversed, I say, and plus the debt to income ratio. And I did that addition, simply added them to combine those two factors. And then I did the 3.5 transformation. And then I just carried over the outcomes. And here you see the sum, the transform, and then to get the probability, I need to add up cumulatively, add the outcomes, the zeros and ones, starting at the lower data of the set point of minus 3.5 and increasing to the plus 3.5. So doing that allowed me to make the probability curve. And this is a curve of the cumulative outcomes divided by and plotted against, and then the blue lines are the outcomes, zeros and ones, and the probability added to that. All right. So here you can see that by the data, and that's simply these columns. These columns were separated and sorted in order of the transformation. So here they are unsorted, you see. So after that, going through and explaining the data, now I'm going to explain to you the area under the curve, or the ROC curve calculations. Well, let's see, first of all, let's look at the ROC curve. There's the receiver operating characteristic curve. And it has an area under this turned to be a pretty good model. It's got an area under the curve equal to 0.81, which is pretty good. And there again, like I say, it's using the model of years at employer reversed plus the debt to income ratio. And didn't even use age, which you would think would have been necessary. And maybe it could have been improved upon, but just to develop the spreadsheet, we were mainly interested in getting formulas in the spreadsheet correct. So, in input to the problem, we have, of course, our data, the outcome data, and our transformation data. This is the input to the ROC curve calculation. And here's where it calculates the area under the curve. That's just repeated up here. And then in this problem, actually the optimum set point is determined by the costs that are incurred. So we've assigned costs here of a cost per false positive is $2,500, and a cost per false negative is $5,000. And I've also added, we could add cost per true positive and a cost for a true negative. And these are worded in terms of costs, but if they were making you profit, you could put a negative in for these values and still come up with a way to include profit. The minimum cost per event is how you determine the optimum set point. And here we've come up with a minimum cost per event of $525 and threshold at 0.8 for that minimum cost per event. And I think I can show you where that is. Let's see. Here's cost per event in this row 9. And let's just go over and see where we come up with a minimum of 525. Still going down. There's a 525 right here. And you can see the set point is 0.8. And I believe that's what we reported over here. So set point of 0.8, and it automatically finds that for you. Which is kind of nice. Why not let Excel do the work and everything? So now let's just look at the calculation. Doing the calculation, we list all the set points available, and then we figure the true positives at that threshold. We figure the true positive rates at the threshold. We figure the false positives. We figure the false positive rates at the threshold. We figure the area of the rectangle near that threshold. We also have included in this spreadsheet the false negatives at the threshold and the true negatives at the threshold. And then the cost per event takes in these four costs and the values of the false positive and the four factors, and comes up with the cost per event. Our total number of events. Another thing the spreadsheet gives you is the uh, total outcomes that are 1 is 50, total outcomes that are 0 is 150, and the total outcomes is 200. And from those values, we've got a condition incidence in the training set of 25% are ones and 75% are zeros. A 1 is taken to be a default on a credit card, and a 0 is customers who did not default. And let's just go through some other this. These stuff are reported are really handy because they're asked in some online courses of what the values are. So the base rate cost per event is $1,250, and that is if you didn't have a model. And there you can see the calculation for that. It's simply the total number of outcomes that are 1 uh, times the cost per false negative, or cost per 1, which is $5,000, divided by BO13, which is the total number of outcomes. And so that gives you the base rate cost per event. So if our model is doing any good, we reduce the cost. Now, we said over here that the minimum cost is $525 when we make our threshold 0.8. So we make our threshold 0.8, and our cost then per event is $525, which means incremental value is $725. That's the savings per event. And the cost, if we take we're given data that says the cost for the bank to perform the experiment to get the data, if it was $750,000, and if there's 1,000 applicants per day, that the payback period would be 1.03 days. And some other figures. If we predicted everyone was 1, we would have had 200 ones, and the actual income of ones is 150. This would make the cost per event equal to $1,875. And just some information, a false positive is predicting a 1 when the outcome is really a 0. Therefore, the cost of a false positive is equal to the cost of a 0. A false negative is predicting a 0 when the outcome is really a 1. Therefore, the cost of a false negative is the cost of a 1, which is the credit card problem would have been the cost of a default. So let's look at some graphs we got here. I think I've already showed you well, here's the probability versus the Y's, the outcomes. It's a famous logistic regression graph. And then here we got cost per event versus threshold. And here we've got true positives versus threshold. Here we got false positives versus threshold. And let's go back to this ROC curve. On it, we have, it's actually the false positive rate divided by versus the false negative rate. And that gives us an area into the curve is this area above that curve. So Well, I guess no, it's the area under the curve, this area. And we're at a zero point 0.8 value, 0.8, 0.81, which is really good. A 0.81 value means that we are got a pretty good model for predicting the uh, defaulting customers on credit cards, given that data set. Okay, well, that explains the ROC curve. Uh, it's a little bit more than what I want to get into and explain each cell, but I'll show you where it's available at a website. And for just a minimum fee, you can order the spreadsheet. And the nice thing is, it does give you all these extra factors which are asked in online courses. Okay, that concludes this video.